Okay, let's continue with our effective field theory lecture. And just to continue with our discussion from Monday, let me give some comments. Comments on the application of the method of regens to our example. We started out by guessing something on the structure of effective field theories, including loops, and let me come back to this. After we have performed the method of regens, we can now look at the result and relate it to Feynman rules. So first of all, we did originally a three-level matching of our fundamental theory, which contains one heavy and one light particle, and it is constructed like E plus E minus and Z boson interactions. So at tree level there is such a Feynman diagram in the fundamental theory, and we apply it now to the case where one incoming momentum is 0, the other one is k, and one outgoing momentum is again 0, and the other outgoing momentum is k. Then in the heavy line, k is the running momentum, and if we approximate this to an effective field theory vertex, this becomes 1 over k square minus capital M square, and this can be expanded as a geometric series. I'm ignoring the coupling constant as a prefactor, so we have a sum n from 0 to infinity of minus 1 over m square times small m square over capital M square to the power n. Here of course we have the momentum k square over m square. So three-level matching of our fundamental theory to an effective theory at lowest order produces here a vertex minus 1 over m square. But actually we can perform the matching also at higher orders in the small momentum k. So this is now a small momentum in the full theory, and if we approximate the diagram exactly, then we have a vertex which is a geometric series in the small momentum k. And we have higher and higher powers of k in our Feynman rule, and lower and lower powers like 1 over m square. Yep. No, I just said it because that will be our application. Because now we can look indeed at this Feynman diagram. This exact Feynman diagram where we have momentum equal to 0, and here a loop momentum k. And if we look at this Feynman diagram using that vertex, then we need exactly this momentum assignment. This momentum is 0, and that other momentum is the loop momentum k. And now we plug into the vertex this Feynman rule, which is the geometric series, which is the exact matching at all orders between effective and full theory. Then what is the result of this diagram? That is exactly our soft integral from the method of regens. So up to the prefactors from coupling constants, but this is exactly the soft integral. If you remember, the soft integral came from the full Feynman diagram where we indeed replaced the propagator 1 over k square minus capital M square by this very geometric series. And that gave us the definition of I soft. And so now we see that the effective field theory vertex and that effective field theory Feynman diagram is identical to the soft integral I soft. So that was the diagram that we imagined right at the beginning in our intuitive kind of guesswork. This diagram must exist in the EFT, and now we see that using method of regens there is a one-to-one correspondence between the soft integral in the expansion and the actual EFT Feynman diagram. So this I soft corresponds to an EFT one loop diagram. With a vertex from tree-level matching. So that is very nice. And so you see here once again that the vertex here, the tree-level vertex, is a polynomial in K, and it also would be a polynomial in the small mass. Here the vertex doesn't depend on the small mass, but in general it would have to be a polynomial in all the small quantities. But once we use that vertex and calculate the actual loop diagram, then we get a non-analytic dependence. Is non-analytic in M. Okay, so we saw that from the explicit calculation. And so we see a one-to-one correspondence between one part of the method of regions and our EFT Feynman diagrams. Now let us consider the hard integral in our method of regions, which came from the opposite expansion where the loop momentum was considered to be big, and we expanded the light propagator in the loop. We saw from the explicit calculation that this integral is by construction a polynomial. I mean a power series if we use all orders, but if we truncate it is a polynomial in the light quantities, here in the light mass. Not in the heavy mass, but that is not important. It is a polynomial in the light mass. And now we see that this hard integral, from the point of view of the low energy variables, the hard integral is just a constant. It is a constant, or a polynomial in M. But as written as a Feynman rule, it is a constant corresponding to such a Feynman rule where the blob is just the result of this hard integral. And therefore, we now see that first of all, I soft plus I hard reproduces exactly the two Feynman diagrams that we intuitively expected in our beginning section. (3.1). And from looking at the results, we also can answer some questions that we had in our introductory section. So we get some further answers. So first of all, we see that this Feynman diagram, which is nothing but the hard integral, is a polynomial in M, and it would also be a polynomial in the small momentum if that would play a role by construction.
هنا نجد يعني عكس الفيديو الفات أنا أخطأت في شيء في الفيديو الفات إنه قلت أن الهارد الآي هارد هو بانوميال في الام كابيتال، لكن هو بانوميال في الام سمول أو في الكي، وهذا ما يسمى بالزوم الزوم إن، لأنه نجد أن الكتلة ام ليست ثابتة، ام سمول ليست ثابتة إنما تتغير حسب هذه البولينوميال، والتغير يكون في الكوفيشنت. والاي سوفت عكس تماما الفيديو السابق، اي سوفت نجدها انها تتعلق بالام كابيتال، هذا هو الاي سوفت عكس تماما عن ما ذكرته السابق. اي سوفت لانه الكي نفترضه هو صغير، الكي هو صغير، وبالتالي نجد أن الكي أوفر ام سكوير، كي سكوير ام سكوير هو الذي يكون عليه البولينوميال. البولينوميال هنا ماذا يعني؟ بولينوميال كما ذكر المتحدث في فيديوهات سابقة إنها لديها خاصية أنها كلما ما ذهبنا للهاي ليفلز فإنها تؤول إلى الزيرو، يعني هي كونفيرجنت. هذه هي البولينوميال. ولدينا ولديها خاصية أيضا جميلة جدا أننا يمكن أن نفعل ذلك، يعني يمكن أن نجعلها كونفرجنت وممكن أن نجعلها يعني تؤول إلى الزيرو بتعديل الكوفيشنتس. يعني إذا جرينا اشتقاقات لأي بولينوميال بأننا تعطينا نفس البولينوميال لكن تنقص الديجريز بتاعها. يعني مثلا لدينا اكس سكوير زائد اكس زائد اكس سكوير زائد اكس كيوب مثلا. إذا جرينا التفاضل فإننا اكس ستكون عبارة عن واحد، واكس سكوير ستكون اكس واكس كيوب ستكون اكس سكوير، وهكذا. بالتالي البولينوميال نستطيع أن نغير يعني يمكن أن نجري عليها مع إجراءات التفاضل، ويمكن أن نغير عليها الكوفيشنت بحيث أن نجعلها تؤول إلى الزيرو. لكن الإشكالية أن البولينوميال يعني الإكس ذاته يجب أن تكون شنو؟ لا تكون، يجب أن تكون عنصر رقم صغير، لأنه رقم صغير عندما تضع فيه أسا فإنه يكون أصغر. يعني مثلا نص تربيع يدينا ربع، وربع تربيع يدينا 1/16، وهكذا. يجب على البولينوميال تكون صغيرة. وبالتالي ما نفعله هو أن نجعل هنا نجعلنا أن كي في السوفت جعلنا كي أقل من الام. في الهارد نجعل الكي أكبر من ام سمول، بالتالي نعمل ام سمول على كي، ام سمول سكوير على كي سكوير. هنا الكي أقل من ام كابيتال، بالتالي عملنا كي سكوير على ام سكوير تربيع. هنا في السوفت بما أننا عملنا كي صغيرة، إذا نحن نحسب على ماذا؟ نحسب على ام كابيتال. وام كابيتال دعونا نأخذ مثال أن الزي يعطينا، يعني البوزون زي يعطينا الكترون ماينس الكترون موجب، زي بوزون يعطينا الكترونات. طيب لدينا سوفت انتجريشن وهارد انتجريشن، أو انتجرال، هارد انتجرال وسوفت انتجرال. دي يسمى بالميثود اوف ريجنز. أنا الآن أعيد الفيديو السابق، أعيد الفيديو السابق مباشرة بطريقة أفضل تتفق مع نظريتي. طيب ماذا نفعل هنا؟ لدينا احتمالين. احتمال إنه نجعل الكي اللي هو المومنتوم نجعله صغيرا، وبالتالي طبعا جعلنا كي مومنتوم صغيرا. نحن إذا نتحدث عن ماذا؟ نتحدث عن الزي. نحن الآن نوصف الزي بوزون، نجعل كي المومنتوم صغيرا، ونجعل بالنسبة للام كابيتال، الام كابيتال هي كتلة الزي، فالمومنتوم نجعله صغيرا والزي والام نجعله كبيرا. ثم بعد ذلك نوجد السميشن بالنسبة لهذه البولينوميال كي تربيع على ام كابيتال تربيع كل أسي ان. هذه البولينوميال مفترض أن تكون كونفرجنت لأنه كي على ام صغير. تمام. هنا نعمل ماذا فعلنا؟ عملنا زوم اوت. في السوفت عملنا زوم اوت. لماذا زوم اوت؟ لأنه لم نأخذ التفاعلات الدقيقة في الاعتبار، فقط عملنا بماذا؟ بالكتلة الكبيرة اللي هو كتلة الزي. عملنا الكتلة الكبيرة هو كتلة الزي، وحاولنا أن نعرف ماذا يوجد في الداخل بكتلة الزي. طبعا هذه ربما يكون تختلف قليلا من نظرية علي يوسف، لأن نظرية علي يوسف تقول أن التفاعلات الداخلية أن الكتلة تكون صغيرة ثم تكبر كلما ذهبنا إلى الخارج، خارج التفاعل. وبالتالي هنا نجد أنها تأخذنا إلى نهايات خارج التفاعل، أنه أن الزي تأخذ كتلتها، طبعا زي كتلتها كبيرة 90 جيجا إلكترون فولت، يعني ولا 95 جيجا إلكترون فولت، يعني مقابل الإلكترونات هي 500 كيلو إلكترون فولت، أو نص ميجا. الإلكترون الواحد نص ميجا، الإلكترونين الاثنين 1 ميجا. يعني انظر إلى الحجم صغير جدا الإلكترونات مقابل الزي بوزون. وبالتالي ماذا يحصل؟ في هذا النوع من الانتجريشن هو عملنا انتجريشن بالنسبة للمومنتوم الصغير للزي وكتلة الزي الضخمة. طيب هذا بالنسبة للسوفت. وفي نظريتي يعني عملنا زوم اوت، أي اعتمدنا كتلة الزي، وبالتالي ما نفعله هي حسابات معينة من أجل حساب كتلة الزي، ولا نعتبر أشياء أخرى. هذا ما أعتقده. هذا بالنسبة للسوفت. لكن نجي للهارد. يعني السوفت يبين لنا ما يسمى باليو في يو في كومبليشن. نعم اليو في. لكن تعال للهارد. الهارد هنا، الهارد ماذا فعلنا؟ الهارد فعلنا انه جعلنا الكي عالية، الكي جعلناها عالية، وبالتالي المومنتوم اصبح عالي. طيب المومنتوم ماذا هذا؟ مومنتوم الزي ايضا. يعني حاولنا ان ندرس الزي بوزون بدلالة المومنتوم وليس بدلالة الماس، وبالتالي عملنا دالة بين ام سكوير على كي سكوير، لكن ام ماذا؟ ام سمول. وام سمول قلنا هي تكون ماذا؟ يعني مثلا تكون الكترونات ايضا مع بعض، الكترون وبيزيترون مع بعضهم البعض. طيب في حالة الهارد هذه هنا يعتبر اي ار انتجريشن. سنرى هذا في المستقبل، ربما سنعدل، ربما يكون صحيحا. هاي اي ار انتجريشن. لماذا؟ لأنه نحن دخلنا بالداخل. في نظريتي نقول زوم ان، دخلنا بالداخل، حاولنا أن نشوف هذه المومنتوم العالية. يعني مثلا نمثل الكواركات، نجي نمثل الكواركات لديها مومنتوم عالي، لديها كتلة قليلة، وبالتالي إذا عملنا بولينوميال ام على كي سكوير، ام سكوير على كي سكوير، هكذا نحن نحاول أن نحسب الكي ونتجاهل قليلا الام، ام سمول، وبالتالي هنا عملنا الزوم ان. هذا ما اعتقده في نظريتي، هذا ما اعتقده هنا في نظريتي. وربما تؤدي هذه إلى أن نجعل نحل فايمان دياجرامز ونحل فايمان بروبيجيتورز بهذه الآلية، بحيث الجمع إذا جمعنا السوفت والهارد يعطينا الإجابة زيرو. أي نجعل المعادلتان البولينوميالز الاثنين نجعلها تساوي زيرو، جمعهما يساوي زيرو، وبالتالي حسب نظريتي يمكن أن ندرس كل واحدة على حدة، ولكن حسب ماذا سنرى ماذا سيقول حسب ال EFT. هذا مراجعة للفيديو السابق وتصحيح قليلا للفيديو السابق، وتعال نشوف ماذا يحدث بعد ذلك.
Of the method of region. So this guarantees that this hard integral will always be a polynomial in the small variables, and that is an answer to one of our questions. In the intuitive expectation, we knew that every Feynman diagram, every Feynman rule must be a polynomial in the momenta, and we were asking, can it also be a polynomial in the small mass? And the answer is yes. It is guaranteed to be a polynomial also in the small masses, because this Feynman rule corresponds to the hard integral, which is guaranteed to be a polynomial in all the small variables.
انظر، قال أنا زي قبل قليل قلت نتجاهل الام، يمكن ما نتجاهل الام أيضا، هذا أمر نسيته أيضا. لماذا؟ لأنه نحن عملنا زوم إن، يعني حتى الام كانت صغيرة بالنسبة للكي، فيمكن بتقنية أخرى أن نعمل الأمر كله دالة في الام برغم من صغرها. يعني كي كبيرة وام صغيرة. يعني نمسك الكواركات، الكي كمية التحرك لها كبيرة جدا، ولكن الام صغيرة. مع هذا يمكننا أن نعمل نجعلها دالة بولينوميال في ام السمول، لكن مع تغيير الكوفيشنتس. الضمان ماذا؟ الضمان انه يجب ان تكون قيمة البولينوميال كل حد يجب ان يكون اقل من الواحد. هذا هو الضمان. وعشان من اجل ان نجعله اقل من واحد يجب ان يكون البسط اقل من المقام. هذا يقودنا الى ماذا؟ يقودنا الى تأثير الفضاء الثنائي الابعاد غير المتناظر. بس انه في دالة جرين، ارجعوا الفيديوهات السابقة، في دالة جرين او في فايمان بروبيجيتور يجب ان يكون المقام اكبر من الحد بأي شكل كان. لو اصبح المقام اكبر من البسط، لو اصبح البسط اكبر من المقام، وقلنا ماذا يفعل الفضاء ثنائي الابعاد؟ فانه سيفعل الياته للدفاع عن نفسه لطرد الكتل حتى يصبح المقام اكبر من البسط، وهذا ما يظهر جليا في معادلة فايمان، بحيث انه نضع الكتل والمومنتوم كلها في المقام، والبسط نحاول نجعله عبارة عن اي او نجعله عبارة عن واحد. اذا كان اكبر من الواحد واكبر من الاي فإننا نستخدم الآليات المذكورة في الفيديوهات السابقة حتى أن نجعل التحليلات المذكورة في الفيديوهات السابقة حتى أن نجعل البسط أقل من المقام بأي شكل كان. يجب أن يكون البسط أقل من المقام، بالرغم من أننا لو حلينا المعادلة بأن البسط أكبر من المقام ربما نصل لنتائج أفضل. لن نستخدم البرتبيشن ثيوري لأن هذه كلها تدخل في نظام البرتبيشن ثيوري. ربما نطور آليات أفضل، طرق أفضل، بحيث أن نستطيع معالجة البسط أكبر من المقام. لكن في كل الحالات هي آلية واحدة، إذا كان البسط أكبر من المقام فإن الفضاء ثنائي الأبعاد يطرد كتل. يعني إذا جعلت المقام أكبر من البسط ولا البسط أكبر من المقام يجب أن تعبر عن الكتل المطرودة بدلالة هذه الآلية. فربما نقول أنه في البرتبيشن ثيوري وتطبيق في فايمان بروبيجيتور نجد في البرتبيشن ثيوري أن الحد الأول كبير، الحد الثاني أصغر، الحد الثالث أصغر، وهكذا، وكل الحدود أصغر من الواحد. فلكن الحد الأول يعتبر أكبر حد، وبالتالي يمكن تخبرنا الحد الأول تخبرنا الكتل المطرودة الكبيرة، الحد الثاني يخبرنا الكتل المطرودة الصغيرة، وهكذا. أو العكس، تعتمد على الكوفيشنت. فمثلا يمكن أن نستخدم كوفيشنت أقل مضروبة في الكتل، وبالتالي هنا تصبح الكتل أصغر. يعني الحد الأول عبارة في البرتبيشن ثيوري، يعني الحد الأول عبارة عن الكتل الصغيرة المطرودة، ثم الحد الثاني الذي فيه الكوبلينج كونستانت كبيرا، يعني 1/137 تربيع صغيرا، يعني كوبلينج كونستانت أصغر، هذا يعطينا كتلة أكبر. يمكن نعتبر هذا الأمر، وبالتالي تأتينا first generation والsecond generation والthird generation. يعني مثلا في الكواركات first generation هي الأب والداون، السكند جنريشن أظن هو الشارم والسترونج، والثيرد جنريشن هو التوب والبيوتي. نجد أن في تدرج في الطاقة أو في الكتلة من الأصغر إلى الأكبر. ربما يكون هذا الأمر، فالأمر يعتمد على الكوفيشنت، لكن كله ينطبق مع نظريتي، ينطبق بصحة مع نظريتي أن إذا جعلت المقام أكبر من البسط فهذا يعني أنك تحافظ على الفضاء الثنائي الأبعاد غير المتناظر أكبر من الكتلة أو الطاقة المكثفة، وبالتالي يمكن أن تجعل الكتل الصغيرة المطرودة في هذا المقام في الفضاء الثنائي الأبعاد غير المتناظر، أو في بيئة الفضاء الثنائي الأبعاد غير المتناظر. وإذا جعلت البسط أكبر من المقام أيضا يجب أن تعبر عن الكتل المطرودة بهذه الآلية أيضا. فكل الحالات نظريتي صحيحة في هذه الأمر، لكنهم هم يعتقدون أن حتى يطبقوا البرتبيشن ثيوري بكفاءة يجب أن يطبقوا فكرة أن المقام يجب أن يكون أكبر من البسط، ويعوض الكتل المطرودة كلها في المقام. يعني من أجل مثلا تساوي البسط من المقام مع المقام، تساوي البسط مع المقام، إذا M والبي السمول الاثنين موجودات في المقام، أو M كابيتال موجودة في المقام، عبارة عن الكتل المطرودة من المعادلة أو من التفاعل. هكذا ربما يظنون الأمر، لكن أيضا تتفق مع نظريته ولا تختلف معه. طيب تعالوا نواصل.
So that answers one question. Second, it arises from the loop integral, this hard loop integral. And by construction, this loop contains only one physical scale, namely the hard scale. Therefore, the structure of the loop integral is of the form some constant divided by epsilon plus the same constant times ln mu square. And now we know what is the second dimensionful variable in the logarithm to make the argument dimensionless. It can only be the hard scale because the loop only depends on the hard scale. So that is now the new result, which we didn't know in the section 3.1. So this answers a second question, namely we now know that the logarithm which arises in this Feynman rule,
انظر هنا نجد أن في الهارد هذا الأمر طبعا قريب مما ذكرته، أنه نجعل ال A يساوي A على إبسلون. A طبعا إبسلون صغيرة، بالتالي A ستكون كبيرة، زائد ال A مضروبة في اللوغاريتم يو تربيع على M تربيع. هنا عوض بدل K عوض M كابيتال، لكن هو سنتعرف على هذه القيمة ماذا ستكون. طبعا اللوغاريتم لديه خاصية أنه يصغر ثم يكبر، يعني مثلا من ما لا نهاية إلى الصفر هو يصغر، من الصفر إلى ناقص ما لا نهاية هو يكبر آخر، أو من ما لا نهاية إلى الواحد، من ما لا نهاية إلى الواحد يصغر، من الواحد إلى الصفر يكبر مرة أخرى، هكذا على ما أعتقد اللوغاريتم. وبالتالي يمكن إذا اعتبرت بهذه الطريقة أو بهذه الطريقة الأمر أيضا يجري. يعني إذا عملت الميو أصغر من M كابيتال فإن اللوغاريتم يكبر أيضا لكن بعلامة ناقص، وإذا جعلت ميو أكبر من M كابيتال فإن اللوغاريتم أيضا يكبر بعلامة موجب. هذا يعني ربما أن هو يقصد ذلك، ربما يقصد ذلك، لكن الأمر سيكون معتمد على ال A. ماذا سيخبرنا على ال A وماذا ستخبرنا الإبسلون، لأن الإبسلون مع عندما نعمل الهارد يعني نحن نتقدم أن أبعادها تصغر، إبسلون ربما تكبر. في نظرية إبسلون بتكبر لأن نحن أبعادنا صغرت، نحن عملنا زوم إن معناته نحن صغرنا ورأينا ما يوجد داخلا، فبالتالي إبسلون لا تصغر وإنما مفترض أن تكبر. أو سيعوض المحاضر شيئا ما ليعوض هذه أو ليوضح هذه الفكرة أن إبسلون تكبر فبالتالي تصغر، ربما هكذا هذا الأمر. لأنه طبعا الخلاف هناك خلاف في المعادلات الرياضية أو في الأفكار. لما يكون هناك خلاف في أفكار معناته تطبيق المعادلات الرياضية تكون مختلفة، لكن النمط للمعادلة الرياضية ستكون متشابهة. في النهاية سنصل إلى نتيجة واحدة، يعني أفكاري أنا حسب نظريتي أو أفكاره هو بمنطلق آخر يجب أن تؤول إلى نفس الخطوات النهائية ونفس النتيجة. جميل، هذا ما سنراه بعد قليل إن شاء الله في هذا الفيديو.
Logarithm of mu must be accompanied only by the hard scale and not by any other scale of the problem. So we can predict the ln mu square over capital M square coefficient from the 1 over epsilon pole of the hard integral. Once you know the 1 over epsilon pole of the hard integral, you know the logarithm of the hard scale. So, and taken everything together, you see that the method of regions guarantees that the effective field theory intuition will work. And we have a very nice classification of the soft and hard integrals into different Feynman rules and Feynman diagrams in the EFT. And so we can say that the method of regions is the basis of the validity of EFT at higher orders. Okay, this is our result. And with this, we have in principle understood the method of regions. We applied it to an example and we see how it matches to the effective field theory way of thinking. Do you have any questions to this discussion? Very good. Then we can now go on and deepen the technical discussion a little bit. I want to show you today some technical details of the loop integrals which help you maybe understand a little bit more why the method of regions works and what kind of technical intricacies of dimensional regularization it relies on. And also to avoid potential mistakes or misunderstandings by applying wrong exchange of limits, as we already discussed in the exercise. So this is going to become a little bit more technical and mathematical even. Let me begin by discussing with you the mathematics of single-scale integrals in dimensional regularization. Let me begin by discussing with you the mathematics of single-scale integrals in dimensional regularization. And let us define here a function f which depends on two variables d and m square, which is defined as the d-dimensional loop integral over k of 1 over k square minus m square overall to the power n. So there are two variables, namely the physical mass scale m square. So m square is taken as one variable, and then the dimensionality d, which appears in the integration measure. And there is actually a third variable n, but let us keep that fixed for the moment. And for simplicity, we take n to be an integer. Actually, one could generalize and take n as any complex number as well, and then we would have a function of three complex variables defined in this way. But let's ignore the n dependence for now. So we have a function of two complex variables, d and m square, defined by that. So we know what the exact result is, namely from our master formula. That is exactly the master formula with index n. And so let me just copy the result. I times mu to the 4 minus d times 4 pi to minus d over 2 times minus 1 to the power n divided by n minus 1 factorial times gamma of n minus d over 2 times m square to the power d over 2 minus n. Okay, now you see the first three factors are kind of uninteresting. They are just standard constants raised to some powers. That is not really interesting. The interesting part is really the combination of these two factors here, the gamma function and the power of the variable m square. So let's highlight this. F of d and m square is proportional up to trivial factors to gamma of n minus d over 2 times m square to the power d over 2 minus n. And this is a mathematical function that one can discuss it is a function of two complex variables, and obviously it is defined in the entire complex plane for both variables. So this is a complex function which is holomorphic almost everywhere. This is also a complex function of two variables which is defined almost everywhere, but not quite everywhere. And both functions have some singularities in the complex plane as a function of their arguments, and that is what we want to discuss a little bit. So study it for d and m square being complex variables. So let me do it in the following way, kind of a more mathematical procedure, which is nice in this case. So let's immediately write down some claims and afterwards prove them. Namely, our function f of d and m square has the following properties. A, it is non-analytic for m square going to 0, with some exception, namely unless d over 2 minus n is a natural number or 0. But in general, it is non-analytic. It has poles for d equal 2n or 2n plus 2, 2n plus 4, and so on. And by the way, both of these properties are obvious. So we will not say much more about this because the non-analyticity is obvious. You know how such a power function behaves. If you have a non-integer power or exponent of this function, it behaves like logarithm of m square. And logarithm of m square is singular at the origin, and that explains this statement immediately. If you have an integer power, then of course it is analytic, but that is an exception. Similarly, the poles come from the gamma function, and we have already discussed that the gamma function has And by the way, both of these properties are obvious. So we will not say much more about this because the non-analyticity is obvious. You know how such a power function behaves. If you have a non-integer power or exponent of this function, it behaves like logarithm of m square. And logarithm of m square is singular at the origin, and that explains this statement immediately. If you have an integer power, then of course it is analytic, but that is an exception. Similarly, the poles come from the gamma function, and we have already discussed that the gamma function has poles at 0 and the negative integers, and that immediately explains this statement here. So that is clear. But let's go on. The function is discontinuous or continuous for m square going to 0 if d is either bigger or smaller than 2n. So if d is bigger than 2n, then the exponent is positive, and if m square goes to 0, then the function goes to 0 continuously. If, however, the exponent is negative, then it behaves like 1 over m square basically, and the function goes to infinity if m square goes to 0. So this explains immediately this statement. And then something less obvious, the derivative with respect to m square commutes with the integral over k. That is something that we have to prove. So you can take the derivative with respect to m square either in the result, or you take it under the integral, then integrate and compare, and you get the same answer. And the final statement is Taylor expansion. That is particularly interesting for us, since that is in the end what we want. Taylor expansion around m square equals 0 commutes with the integral over k. That is kind of clear because also derivatives commute with the integral, but the Taylor expansion vanishes identically. Okay. This is our set of claims. And again, the first three are obvious, and the last two are non-obvious, and we will discuss them now. So this is an interesting mathematical function, in fact, of two variables, m square and this particular combination of t. Even though I say we do not need to prove the statement A and B, but let's visualize it. Let's visualize it by drawing a diagram, two diagrams in the complex plane. So here we have the complex plane of D, here real part of D, imaginary part of D, and here the complex plane for m square, real part of m square and imaginary part of m square. Then we can at least visualize the different properties. So first of all, here at some place there is the value 2n, and then we have here some border, and at 2n there is a pole, 2n plus 2, there is another pole, 2n plus 4, and so on. So here these are the poles of the function as a function of the dimension d. So there is an infinite number of poles and they all go to the right. On the other hand, we can also ask when does the integral actually converge in the sense of ordinary integrals? And then by power counting you can see if the dimension is small enough, the integral converges. So, and obviously the first value where it converges is to the left of this first pole. So basically everywhere to the left of the dashed line the integral converges by power counting. And if then we take an integer dimension, so here integer dimensions, integer but also positive, then these are integer dimensions where the integral converges and agrees with the ordinary integer dimensional integral. And I mean, depending on the value of n, the number of the blue dots might be 0 or large. Here at this origin, of course, the dimension is 0, and for negative dimension there is no ordinary integral. But in dimensional regularization, it would converge, of course, also for negative d, and it is defined for negative d as well. Then, what else can we say? So if we are to the right of the dashed line, the function basically looks like m squared to an exponent, and the exponent here is positive. D over 2 minus n is positive, so we have m squared to the power of something positive. That is why we have a continuous limit if m squared goes to 0. And on the other hand, here to the left, we have m squared to some negative power, and therefore the function goes to infinity if m squared goes to 0. So you can think of like square root of m squared in this case, and 1 over square root of m squared in the other case. This would be the typical behavior of the function. So that proves claims A, B, C. Let us also visualize the behavior as a function of m square. So as a function of m square, if the exponent is not an integer, then it is actually equal to writing the function as exponential of prefactor d over 2 minus n times ln m square. Okay? And for this reason, the function essentially behaves like ln m square. Also, you know, square root of m square is an example, m squared to the power 1 over 3 or whatever. Such functions is what we are talking about. And then in the complex plane, as a function of m square, they have a branch cut. For negative values, they are undefined. So there is a branch cut here. And here at the origin, there is a branch point. So the point where the branch cut begins is unambiguous, and in principle one could move the branch cut elsewhere, but let's put it there. And as we already discussed, the branch point is the point which we are actually interested in, because exactly at this point m square is 0. That is where we would like to do a Taylor expansion. But obviously we see that this is a singular point. So in general there is no Taylor expansion, but as I said, it is approached continuously if d is smaller than 2n, bigger. Okay. So it's approached continuously in the region where the integral is divergent. Okay. If the integral is divergent, then we have here a continuous behavior. If it's convergent, then we have discontinuous behavior. That is obvious, because if the integral is convergent, then we will get a result like 1 over m squared. Okay, so again, interesting properties of this mathematical function, and let us now look at these limits here and the derivatives and Taylor expansions. So first we can also briefly clarify the definition at m square equals 0. So initially that is the definition of our function, but exactly at the value m square equals 0, you might think about how it is defined. And clearly what we know is the limit. Limit if m square goes to 0 of the function f of d comma m square. What is the limit? It depends. So the limit is 0 if d is bigger than 2n, but it is infinity if d is smaller than 2n. Okay. And so the limit is not equal for all values of d. In fact, the limit is discontinuous. If you just look at the limit, then there is a discontinuity of the limiting behavior as a function of d. But now we work in dimensional regularization, and dimensional regularization has the recipe, or basically postulate, that the integrals are always analytically continued from a region where they are defined. That would mean if we want to define the function at m square equals 0 in dimensional regularization, we would go to a region of d where the limit converges and becomes 0, and then we analytically continue to all values of d, which means that we would define the m square equals 0 value to vanish for all d. So by definition, at m square equals 0, we analytically continue from the convergent region, and that means that we define the integral over 1 over k square to the power n. So this is exactly the integral at m square equals 0 exactly. So we set the mass to 0, and then we have exactly that integral, which is a scaleless integral that would be defined to be f of d and exactly a 0 argument, and this is defined to be 0 by analytic continuation. Zero value to vanish for all d. So by definition, at m square equals 0, we analytically continue from the convergent region, and that means that we define the integral over 1 over k square to the power n. So this is exactly the integral at m square equals 0 exactly. So we set the mass to 0, and then we have exactly that integral, which is a scaleless integral that would be defined to be f of d and exactly a 0 argument, and this is defined to be 0 by analytic continuation from the region where it is actually mathematically 0. And that corresponds to the statement that scaleless integrals vanish. They vanish for all d.
حتى نكون في الصورة، طبعا هذا يعتبر في هارد ريجيون، الهارد انتجرال هارد ريجيون. كما ذكرنا ان الهارد ريجيون ان كي تكون كبيرة، بالتالي نجد ان البولينوميال تكون في 1 على كي أس ان، 1 على كي أس ان، يعني يمكن تعتبر ايش 2 3. المهم هي 1 على كي أس ان، وهذا عبارة عن بولينوميال في الكي في الهارد ريجون. يعني نعمل زوم ان، والكوفيشنت يمكن نختارها بطريقتنا طريقة جميلة، ونجعل المعادلة كونفرجنت، وهذه كونفرجنت يعني في النهاية السميشن يساوي 0 حتى نحقق البرتوبيشن ثيوري. إذا أنا ما فهمته من هنا أنه الآن هو في السوفت في الهارد ريجون، هذا ما فهمته أنا.
And just to repeat, that means that the function is discontinuous as a function of d at m square equals 0. It is discontinuous as a function of m square in the region where the limit would be infinity. So if you choose a small d, then the function at m square equals 0 is 0, but the limit of approaching m square equals 0 would be infinity. So that is just a word of caution. That means some limits do not interchange. Even though we stated that many things interchange by construction, like derivatives always commute with the integral, but here you see that this thing would be discontinuous. The limit m square going to 0, that is not continuous. Okay, now let us look at derivatives and these two properties. So derivative with respect to m square of the integral k square minus m square to the power n. And okay, we do the integral first. That gives us our famous function. Afterwards we take the derivative, and so of course we take the result here. So d by dm square of the result, which essentially depends on m square only via m square to this power d over 2 minus n. So we take the derivative of this function with respect to m square, and that is the same as dividing by m square and multiplying with this prefactorial here. So the full result will be containing the factors minus 1 to the n divided by n minus 1 factorial. I omit these factors in the front, which are not interesting. Then we have the gamma function of n minus d over 2. Then from the derivative we have times d over 2 minus n and times m square to the power d over 2 minus n minus 1. The minus 1 comes from the derivative. And here you see that actually something happens, namely what happens in the product of the gamma function with this argument times this factor. What do we get? Yes. So you see we get a gamma function with the argument which corresponds to this modified exponent. So we again get a behavior which looks like our original f, but where n is replaced by n plus 1, both here and here. And also there, because minus 1 appears now to the power n plus 1. Very nice. What happens in the opposite order? Let us do first the derivative of the integrand and afterwards do the integration. So here we get, we literally take the derivative of the integrand, and then of course we get minus n as a prefactor divided by, plus n, because there is also an inner derivative, plus n as a prefactor divided by k square minus m square to the power n plus 1. So that also is exactly the same as the original integral, except that n is replaced by n plus 1 and we multiply by n. So what happens? You replace everywhere n by n plus 1. So that corresponds to this here in the gamma function. You replace n by n plus 1. In the exponent you replace n by n plus 1. In the minus 1 you replace n by n plus 1. But n minus 1 factorial remains because you would have n divided by n factorial. So everything matches perfectly and the two things are exactly equal. So we have established this commutation rule. So let me write this down as a nice statement. D by dm square and the integral over k commute. And that was actually a statement on dimensional regularization in general. Therefore I can say that we have simply confirmed this general statement of dimensional regularization. So they commute as always in dimensional regularization. But note, at m square equal to 0, what happens if we do it exactly at m square equals 0? Does it still commute? Yes, it does. It commutes even if we do this, but always after the derivative we set m square to 0 exactly. If we set m square to 0 exactly, then of course we have everywhere scaleless integrals and everything is 0 on all sides of the equations. The result vanishes again. But it is still correct to calculate the derivative before or after the integral. So it is quite tricky to disentangle which limits do not commute and which limits commute. So that is why I try to state this quite clearly. So here we have something which commutes regardless of whether m square is 0 or not. Now the final statement, which is just a corollary, we do a Taylor expansion around m square equals 0. So let's use again the symbol T A m square. So the index A stands for the order by which we do the Taylor expansion, and this is obviously meaning that we do a Taylor expansion around m square equals 0. Then we know the Taylor expansion means take the derivative with respect to m square and set m square to 0. Okay, and we know the derivatives commute with the integral regardless whether m square is 0 or not. Therefore, obviously, this Taylor operator commutes with the integral. So this can be evaluated before or after integral of k. However, if you want convergence, we didn't check convergence because we don't need to since it's dimensional regularization, but just checking when would it actually converge. So the convergence is true if d is small enough. If we do a Taylor expansion up to the order n, then it is convergent if d is bigger than 2n plus 2a. Otherwise, we have 1 over k square in the integrand, and 1 over k square diverges at k going to 0 unless the dimension is high enough. So, but if d is smaller than this number, then we define the integral by analytic continuation. And regardless of this, the result is 0 because after taking the derivative and setting m to 0, we have scaleless integrals which vanish. And if you want details, then the details are exactly like here. We would set the result to 0 by hand by analytically continuing from the convergent region to the region that we actually want. The result is so. Okay. However, if you want convergence, we didn't check convergence because we don't need to since it's dimensional regularization, but just checking when would it actually converge. So the convergence is true if d is small enough. If we do a Taylor expansion up to the order n, then it is convergent if d is bigger than 2n plus 2a. Otherwise, we have 1 over k square in the integrand, and 1 over k square diverges at k going to 0 unless the dimension is high enough. So, but if d is smaller than this number, then we define the integral by analytic continuation. And regardless of this, the result is 0 because after taking the derivative and setting m to 0, we have scaleless integrals which vanish. And if you want details, then the details are exactly like here. We would set the result to 0 by hand by analytically continuing from the convergent region to the region that we actually want. The result is identically 0 because of scaleless integrals. So as a summary, we have the following box: p, m square and a of integral k 1 over k square minus m square to the power n is the same as t a m square 1 over k square minus m square to the power n, which is identically 0. But that is of course different from the integral 1 over k square minus m square to the power n. So what I want to say here is that we can do a Taylor expansion before or after the Taylor expansion vanishes. But if you compare the Taylor expansion with the actual integral that you have Taylor expanded, then the integral is different from the Taylor expansion. That means the integral cannot be Taylor expanded. The Taylor expansion does not converge against the actual function. So all of this is just a little bit more details on things that we have already used, because all of this has been made use of in our discussion of the method of regions in the last lecture. There it was appeared in the form of the A0 function, which has exactly this property. And we use the A0 function explicitly, but here I just pointed out a few more general statements and made it maybe to disentangle a few of those statements. So do you have questions to this analysis? Otherwise, so that is a mathematical interlude. So and I hope that this can serve as a kind of reference whenever you encounter some contradictions or you are unsure which limits you should take in what order, then I think this is a point of reference for such questions. Yep. In principle, first of all, it is sometimes a good idea to also look at the limit d going to infinity or to 0 or some values like that. And maybe this can help also in calculating integrals and then doing the analytical continuation to d equal 4, starting from d equal infinity. So it is a good idea to consider this limit. But here I do not see that anything particular would happen. For sure, when we say the integral is analytically continued to all d, and for example the scalars integrals vanish, then they would of course vanish also in the limit d going to infinity. So here I do not see anything particular coming out of that limit. But in general, it's actually also useful to look at this. Let me apply these insights to one-scale integrals to the more interesting two-scale integrals very briefly. So clearly, just as an obvious remark, all of these above properties matter for the method of regions. So all of these things with Taylor expansion at 0 mass, where we have a branch cut and so on, this is exactly properties which go into the validity of the method of regions. And so now let's come back to our example of this particular integral, which was 1 over k square minus small m square times 1 over k square minus capital M square, which has an exact result I over 16 pi square times a0 of small m divided by m square minus capital M square minus a0 of capital M divided by the same denominator. And the final integral I could be written as I soft plus high hard. So, and there is of course this correspondence here. Now what I simply want to say, following from the previous single scale discussion, so we have now split our two-scale integral into a soft part, which is a one-scale integral, and a hard part, which is also a one-scale integral. So let us just comment here. The soft part is now non-analytic in the small mass square. We already know that. And now we summarize in addition the Taylor expansion with respect to small m square of that result vanishes identically, because that is a function of this form m square to some fractional power, which vanishes identically in dimensional regularization. And but on the other hand, if we do the other Taylor operator, where we regard the capital mass as big, and we do a Taylor expansion in 1 over the capital mass square, then the result is analytic in the capital mass here, and the Taylor expansion with respect to capital M of this, of course, converges to the true result. So we can say in a formula, this operator acting on the soft integral is equal to the soft integral. So we know what both Taylor operators do, namely this Taylor operator maps it to 0, the other Taylor operator maps it to itself. And for the hard integral it's the opposite. So maybe let's just say it's the opposite. So this Taylor operator maps it to 0, and the other Taylor operator maps it to itself. And also, just from looking at these equations from this point of view, we can once again from this viewpoint understand what the method of regions is doing. Namely, we take the fundamental integral that we are interested in, and we can write it as the Taylor operator with respect to the small mass of itself plus Taylor operator with respect to the large mass of itself. And then each time that is actually a sum soft plus hard. It maps the soft part to 0, the hard part to itself. This maps the hard part to 0 and the soft part to itself, and in the end we get the sum is equal to the left hand side. So both T's can be evaluated under the integral dk and reproduce the method of regions. So now we have looked at it from almost sufficiently many points of view. So I think now you are kind of familiar with the example. We did it from so many angles, and but the example is typical of the method of regions, and I think now you can transfer from this to any at least one loop integral and apply the same method of regions expansion, and you know what happens, what kind of objects appear, and also why it works. Now we go on, and I will get more light on the method of regions, but maybe going a little bit away from the example and using some other formalisms which give you also further intuition. I want to give you two reformulations of the method of regents, or in other words, the construction of effective field theories if we have loops. And the first is from the path integral. We already used the path integral to give us a reason why effective field theories exist and how they can be constructed. And we did it at tree level, which is equal to the classical level, where the path integral amounts to solving the equations of motion. Nevertheless, the path integral gave us this intuition that by using equations of motions for the heavy fields, plugging in the solution into the Lagrangian, we obtained the EFT Lagrangian that came from the path integral. And so now let us go back to the path integral and see what it can tell us if we include loops. In other words, if we just take the path integral exactly without going to the classical limit. We start in the same way as in our section 1.4 on tree level, and we look at a green function with light external fields, and we want to compute this green function in the fundamental theory. And the outcome will be that the computation can equivalently be done in an effective field theory with an effective theory Lagrangian. And today we will do the calculation in such a way that we do not use equations of motion, but we take into account all of this. First of all, we need to say that we consider here not only light fields, but the light fields also are allowed to have only small momenta. Otherwise, it is quite clear that the effective field theory description will not work. So let's only allow small momenta for the light fields, and then the path integral formula for it is a path integral over all the light field configurations times all the heavy field configurations, then these light field variables, and e to the I times the action of the full theory. So that is the completely general result. Now we do something which we didn't do in the classical limit. We decompose our field configurations of the light fields as follows. Decompose the light field configurations. Every light field configuration can be written as a sum of a soft light field configuration plus a hard light field configuration, where the difference should be defined precisely somehow, but such that the soft field configuration contains only small momenta, and this contains only large momenta. It is clear that in Fourier space, of course, you can do a cut, and the light modes are contained in LS, the heavy modes are contained in LH, and you can, of course, uniquely split every Fourier decomposition into these two parts, and then you can go back to position space if you want. So there you can set up a unique decomposition where for every field configuration there is a unique decomposition into the two parts. Similarly, we can do it for the integration measure. dl will become an integral over all soft field configurations times all hard field configurations. And then this corresponds to propagators of the light field, and here in the propagator there flow large momenta, here there flow small momenta.
طبعا هنا نلاحظ أنه الآن رجعنا للفيزياء، يعني ما قيل لحد اللحظة أو لحد هذا العنوان ما بعد الرياضيات وآليات رياضية. الآن رجعنا للفيزياء، إنه قسم الكونفيجريشن بالنسبة لللايت فيلد إلى قسمين، السوفت والهارد. نأتي مرة أخرى الهارد طبعا هو يعتمد المومنتوم لم يعتمد الكتلة، فقال إنه السوفت السمول مومنتوم والهارد اللارج مومنتوم. وإذا الهارد زوم إن بالنسبة لنظريتي زوم إن، والسوفت زوم أوت. طيب تعالوا نشوف إلى أين يؤدي هذا. طبعا زوم إن يعني اي ار كومبليشن، وزوم اوت يعني يو في كومبليشن. طيب يعني في اليو في نعتمد على السمول مومنتوم، وفي الاي ار اللارج مومنتوم. طيب تعالوا نشوف الى اين يؤدي بنا هذا الامر.
So large or small momenta in the light field propagators. Therefore, the left-hand side of our expression now becomes a green function where we only have the LS variable, because we by definition allowed only small momenta. So on the left we can only have these LS field configurations, and the path integral formula would now be the following integral: an integral over the soft light fields, an integral over the hard light fields, and the heavy fields. And then let us put the field variables here, LS, LS. They depend only on the light field, so they can be pulled out of the integral over the heavy modes and the hard modes. So the field variables are here, and here we have e to the I times the full action. And now we see something, namely all of this bit here.
نلاحظ أنه يتحدث عن الجرين فانكشن اللي هي بسط المقام. البسط يجب أن تكون أقل من المقام، وإلا الفضاء ثنائي الأبعاد لم يقبل هذا الأمر. الآن هو يتحدث عن الانتجريشن الأكشن عن طريق دالة جرين، بالتالي يجب أن تنطبق نظريتي في هذا الأمر. طيب تعالوا نشوف.
Is an integral is a path integral over two variables h and lh, which can be done once and for all. So we can integrate out the heavy fields and the hard modes of the light fields with this exponent, and the result will be something, and the something can then be integrated over the soft modes, and it will look like a path integral for an effective theory which contains only soft light fields. So we can integrate out L, H and H. And we can simply give a name to the result. The result will have this form, dLs of all these ls variables, and then times the result of this, and the name is just e to the I times wh of ls. So this e to the I wh of ls is just the name for the blue box. wh of ls is some functional of ls. Very nice. So this looks like an effective field theory already, and this wh of ls would be the action of the effective theory, and then we are basically already done with a small issue, but essentially we can already say that we can calculate our green function that we want in an effective theory where the path integral contains only the ls field variable, and the action of the effective theory is the wh of ls. Very nice. So this looks like an effective field theory already. And this WH of LS would be the action of the effective theory. And then we are basically already done with a small issue, but essentially we can already say that we can calculate our green function that we want in an effective theory where the path integral contains only the LS field variable and the action of the effective theory is the WH of LS. Now the small issue is the question, what kind of object is that? We would like to have that it is the Lagrangian or an integral over a Lagrangian of an effective theory. But here it is the outcome of some path integral. The outcome of a path integral normally is not a Lagrangian. But we can approximate it to be effectively an integral over a local Lagrangian. And this is what we now need to discuss a little bit. So let us discuss the Feynman diagrams for this object.
هو يقصد ماذا؟ يقصد الاكشن للهارد انتجرال معه الدي اتش كابيتال والتي يسمى بالهيفي فيلد كونفيجريشن بالاضافه الى الاكسبوننشال والاكشن اوف اكسبوننشال الذي او اللاجرانج اوف اكسبوننشال الذي يحتوي على الفول ثيوري. هذا مقصودهم. لكن نحن الآن في الهارد يعني زوم الهارد زوم ان والسوفت زوم اوت، وبالتالي الهارد يعتبر اي ار كومبليشن والسوفت يو في كومبليشن حسب نظريتي انا. وبعد يعني هو الآن يتحدث عن الهارد او الاي ار كومبليشن او الزوم ان. هذا ما اريد ان اقوله. طيب تعالوا نشوف ماذا سيخبرنا.
Now we need to understand how are Feynman diagrams connected with the path integral, and here I will probably drop some results. I think we have discussed almost enough about the path integral in past lectures, but maybe some of the points are not totally obvious, but let me write down everything that we need to know. So first of all, evaluating the path integral corresponds to calculating all Feynman diagrams, of course. And so if we just evaluate this path integral here, then the blue box, it doesn't know about this prefactor here. So the blue box does not correspond to green functions with these external lines. The blue box only corresponds to Feynman diagrams where we have no explicit field variables in front of the action. What does it mean if we just have Feynman diagrams without explicit field variables here? These are vacuum diagrams without external lines. But
جميل جدا. يتحدث عن without external lines، يعني كما ذكرنا الآن نحن نعمل زوم إن، لا نتحدث عن الاكسترنال، ولما نتحدث عن الفيرتكس ونتحدث عن الفاكيوم انرجي، وهذا ما يسمى في نظريتي يسمى بالاي ار او نقول عليها الزوم ان. او ايوه نلاحظ شيء مهم جدا، ان عندما نقول الزوم ان الكميات والابعاد يجب ان تكون كبيره، كتل كبيره، مومنتوم كبير، وثاني ماذا طاقة عالية. الكتل ربما تكون طاقة صغيرة ما عدا كتلة اتش الهيفي فيلد على ما أظن، لكن كتلة اللايت فيلد يكون صغير لكن المومنتوم لها عالية، مثل ما الكوارك داخل البروتون. كتلته صغيرة لكن المومنتوم له عالية. هذا ما نقصده بالزوم إن. زوم إن يعني لا يعني بالضرورة أننا دخلنا جوا، لكن يعني أننا شلنا الصورة وكبرناها بحالتها هذه، لأنه لو دخلنا جوا ربما هذا ما يعني هذا ما أقصد أنه لو دخلنا جوا طبعا الأشياء ستتغير، ستتحول الفيزياء طبعا فيزياء كلاسيكية، ومع الكتل الكبيرة ستكون هناك إشكالية، لأنه ربما هذا ما أقصده. أنا طبعا أنا أستبق الأحداث الآن. ربما هذا ما يقصده، لكن إذا نحن دخلنا جوا صغرنا أبعادنا فممكن تشبيه الأمر مثل أننا كنا في أبعاد ضخمة مثل أبعاد الشمس، ثم صغرنا أبعادنا للأبعاد الحالية وجلسنا فوق سطح البروتون مثل ما نجلس فوق سطح الأرض. فبالتالي نرى أن حركة الإلكترونات مثل حركة الكواكب، كواكب المجموعة الشمسية، حركة بطيئة جدا. هذا ما يسمى يعني إنقاص الأبعاد. سنرى هل يقصد هذا، يعني النتائج التي ستحصل عليها هل يقصد هذا أم يقصد أنه نعمل نصغر نعمل سناب شوت ونثبت الصورة ونعمل لها زوم إن، أو يعني ندخل جوا الصورة إذا ثبتنا هذه الصورة نجد المومنتوم عالي، نجد كتلة لللايت فيلد كتلة صغيرة، للهيفي فيلد كتلة كبيرة، مومنتوم للهيفي فيلد بسيط، المومنتوم لللايت فيلد عالي جدا، والفيزياء تتحول إلى فيزياء كلاسيكية. طيب تعالوا نشوف.
The action of this path integral here, which is the full action of the theory, it contains the hard field, the heavy modes of the light field, which are integrated over. So for them we would have usual propagator Feynman rules, Feynman diagrams involving lines corresponding to these two, but the LS is not integrated over in the path integral. That means, quantum mechanically speaking, the LS is not quantized. The LS is just taken like a classical field variable, which has some value, some classical field configuration value, which is fixed. It will be integrated over afterwards, but in the blue box, the LS is just some classical field. Therefore, we have here vacuum diagrams in a theory where the Lagrangian contains dynamical quantum fields, and in the vertices there appear vectors corresponding to some classical field configuration. You can imagine this like that would be a coupling constant which happens to be x-dependent. It is like an x-dependent coupling constant. If you view it like this, then you should simply say, write down all vacuum integrals, vacuum diagrams in this theory, treating the LS as a local coupling, not different from any other coupling. Then what you should also know is, okay, so let me write this down first. Vacuum diagrams, LH and H propagate. That means only large momenta in the L lines, right? So if we have a line of a light field, then it must carry large momenta because of the LH configuration. And then if you evaluate the path integral and you construct the WH, that the e to the IWH, that would be the full result of the path integral that contains disconnected Feynman diagrams. But if you then work out the WH, the exponent, or in other words the logarithm of the full path integral, then you only get connected Feynman diagrams. This is a general statement about the relationship. So only connected diagrams contribute to WH of LS. The Lagrangian is L full of LS, LH, H. LS is treated as classical field with a fixed value, that is. And if you treat this LS just as a classical field, then it appears as a factor at some vertices. So you could say it behaves like an external field in the diagrams. It can only appear as an external field. It is attached to some vertices, but it cannot propagate. There is no propagator corresponding to the LS. Or acts like external LS lines. So from the fundamental path integral point of view, it would be vacuum diagrams with a local coupling LS, but the equivalent point of view is that these are Feynman diagrams where you have LS as external field and LH and H appear only as internal fields. Then, in general, this is all we know. Connected Feynman diagrams, but now we can draw a conclusion, namely the conclusion is that the diagrams that fulfill these properties must be one particle irreducible with respect to the L lines. And why do they have to be one particle irreducible with respect to the light lines? Because the light lines carry a large momentum. If the diagram would be reducible with respect to the light lines, it would mean that we can cut a light line and make the diagram disconnected. If a diagram becomes disconnected by cutting one light line, then it would mean that all the external lines carry only soft momentum, but the line that we have just cut contains a hard momentum. Then momentum cannot be conserved in such a disconnected piece of a diagram. Many soft momenta flow in. You have cut one hard momentum. There the soft momenta cannot flow out. Therefore, the diagram cannot be cut by cutting a light line, and therefore the diagrams must be one particle irreducible with respect to the light lines. So maybe to illustrate it, this is something that we had in our tree-level matching. Okay, so is this a diagram which is allowed in this sense? It is allowed, it is connected, and it contains only external LS lines and an internal hard lines, and this is not one particle irreducible. It is reducible, but that is okay. If we cut this diagram in two, then momentum can be conserved. We would have here a soft momentum coming in, and the heavy line carries a soft momentum, which is possible. However, look at this diagram. So in some other theory, there might be here a triple vertex, light lines with soft momentum, and here now a light line with a hard momentum. That would be a one particle reducible diagram with respect to the hard light line, and that cannot work because now momentum cannot be conserved. Here a soft momentum flows in and a hard momentum would have to go on. Therefore this diagram doesn't exist. It is zero by momentum conservation. And such diagrams are the ones which are excluded by this statement. So this is impossible. Let's write down a possible diagram with a hard light line. A possible diagram would be this one. Our example. Here our example, we start with a soft light line we have here a heavy particle in the loop, and here we could have a hard light line at the top. Then this is one particle irreducible with respect to the light line, because if we cut the light line, the diagram stays connected, and momentum conservation can work. Namely, if we require that here is a soft momentum, here is a hard momentum, then momentum conservation simply tells us that in this case we must have a hard momentum here as well, which is possible. So these diagrams are possible. These diagrams are possible, but such a diagram is impossible. So, lo and behold, this is our list of properties. We have one particle irreducible diagrams with respect to the light lines, otherwise connected with respect to the heavy lines, and we only have external soft light lines. This is the kind of diagrams that we need. If you now look globally at all such diagrams, no matter how many loops they have, then you see that all of these diagrams admit a Taylor expansion in a kind of obvious way. Here you have a propagator of a heavy field and soft momentum, so you can clearly do a Taylor expansion of this propagator, and it becomes 1 over m square and higher orders, as we already did. That is impossible. And here in this particular case, for this configuration, all the loop momenta are large, and here we also have a large mass. Here we have a small mass but a large loop momentum. So that means all propagators that appear in the Feynman diagram have a heavy scale compared to the soft scale, and that means again we can do a Taylor expansion of this diagram in the small soft quantities. And if we do a Taylor expansion of all these diagrams, then each of the diagrams becomes a power series in the small momenta and the small masses of the problem. And then it means that this entire functional WH of Ls can be written as a power series in the small momenta and small masses of our light theory. And that means it can be expressed as a local Lagrangian corresponding to the EFT. WH of Ls can be written as a local integral of a local EFT Lagrangian. So, and the outcome of this is, of course, that it establishes the existence of an EFT, also including loops. And probably you also discover a similarity to the method of regions. Because we have split the light lines into soft light lines and heavy light lines, and in this way we obtain diagrams where the light line either carries a hard momentum or a soft momentum. In this case, for example, it carries a hard momentum, and this would correspond to one of the two integrals in the method of regions. In this case, it would correspond to the hard integral, which gives us a local Feynman rule in the EFT, as we discovered already. And this is also the statement here, namely this hard part of the loop can be written as a term in the WH of Ls, which can be expanded to give a local Lagrangian. And before we saw that this the method of regions would be interpreted in this way. So this fits perfectly. And diagrams where here you would have an LS, they are not part of the WH. They would only be part of the EFT when you integrate also over the LS field configurations. So when you make the LS field propagate, that is part of the EFT. So this path integral point of view gives us again confirmation that effective field theories exist, and it also has similarities to the method of regions. Therefore, you can view it as an intuitive explanation why it all works. But it's technically not exactly the same, because obviously, again, we have here some kind of a cutoff, a momentum cutoff, an explicit cutoff which tells whether momenta are small or large. And that would mean that loop integrals in this WH of LS would have to be carried out only with heavy loops. That is a cutoff in the loop integration. So this is not the same as doing dimensional regularization. But nevertheless, it's an intuitively nice way of looking at it. So maybe let's apply this to the example to make these remarks more explicit. So the L full contains only this particular interaction, like E plus E minus to Z. Then the diagrams for WH of LS, what are they? So the first diagram is indeed this one here that we had at tree level. And by Taylor expansion, this becomes this effective vertex. Second, we have this loop diagram where we have a hard line and a light line, however, with hard momentum. So, and first of all, this is like the I hard in the method of regions, though not exactly equal, as I just said, but it becomes, by Taylor expansion, such a vertex in the effective theory. We gave it a label one loop in the last lecture. So continuing, we now go back to the full path integral. This part of the calculation, the blue box basically, gives us a Lagrangian for the effective theory by expanding the WH of LS. So now we have a Lagrangian, in other words, we have a set of Feynman rules for the EFT. Now we have calculated the blue box, and then we can calculate the full path integral for the actual green function that we are interested in. So let's see how that goes. Hence, for if we do the full calculation of this example, we have two external light fields, and in the loop we now take the full theory. That means in the loop we can either have here LS or LH, we can have both. We get the following. We get the LS of LS times e to the I WH of LS. Okay, so this is now the effective field theory description of this result. Here I put the result of the blue box, and the result of the blue box is the collection of these two Feynman rules, and therefore in the effective theory this becomes this path integral, and we now evaluate this path integral in the usual way. That means we calculate all Feynman diagrams corresponding to two external LS with the Feynman rules from here. And therefore we get two diagrams. Namely, this one, using that vertex, where we have now only ls in the loop. So this is a loop in the effective theory coming from that path integral. So in the loop there propagates only the ls with soft momentum. And obviously this is like the I soft in the method of regions. And on the other hand, we get this diagram with the one loop vertex, and there is nothing else to calculate here. And this is obviously like the hard integral in method of regions. So very beautiful correspondence again. I already pointed out the difference, so let me write it also here. The difference is that in the method of regions we use dimensional regularization, and in practice it means that we always integrate the full d-dimensional momentum space without cutoff, but here we would have to use a momentum cutoff. So we should restrict the integral to something like k smaller than lambda or k bigger than lambda. So technically it's a little bit different, but anyway it gives us a good intuitive understanding of the entire structure which has emerged. So in total, let me write this nice summary sentence. This provides an intuitive explanation. Why the method of regions works and why EFTs exist. Satisfied? Any comments or questions? So, question. In the classical case, where we used only tree-level diagrams, we did kind of the same logic. And of course, we didn't need to go to this level of detail. But at the blue box, basically, we simply said we can evaluate the path integral by the classical limit, which means we replace the exponent just by the exponent evaluated at the equations of motion for the heavy fields. Very nice. Otherwise, the logic was the same, but there was another fine detail which is different in the construction of the blue box. Who remembers or who can see the small difference? Yep. Yes. We didn't do this in the other case. But here we decomposed the light field into soft plus hard. This decomposition into soft plus hard gives rise to this very nice correspondence to the method of regions. So you see it here. Soft light field becomes a diagram in the EFT. Hard light field becomes a diagram in the matching, becomes a diagram in the blue box, corresponding to the soft and hard region in method of regions. But why did we actually have to do it today? What would happen, or why did we not just do the same as the other time? Just integrate over the hard modes and keep the full L dependence in the EFT. Yes. That is true, but we could still say, okay, we allow by hand that only soft momenta are present on the left-hand side of the equation, but still in the blue box only integrate over the hard field. and not integrate over the hard modes of the light field. The Taylor expansion, that is the point. So here, all such diagrams admit a Taylor expansion. That wouldn't be true if we would not integrate over the hard fields. So because here, that would then not be part of the WH, it would be part of the EFT. And then the remaining diagrams that we would have in the WH, they would not have always a Taylor expansion. And that is the problem. So we would have non-local terms in our Lagrangian. That is the reason why we need to introduce the LH here in the EFT. Did I make a mistake in the explanation? I think I said it somehow incorrectly, but I mean definitely that is the point. So we need to integrate out also the hard modes of the light field in order to be able to do a Taylor expansion of all diagrams. That is exactly the point. And that is why we have this additional step, but the additional step gives us the correspondence to the method of regions. Okay, so now I think we have looked at yet another angle on the construction of EFTs. And next time we will do the final angle, which is yet another reformulation of the same thing, just that you have heard all different formulations, the so-called large mass expansion algorithm, which is equivalent to method of regions, but formulated in a slightly different way. And so you have also another practical tool that you can apply in calculations. And then we do really physics applications. Probably we will do an application to G-2 of the muon, where we can understand how different Feynman diagrams contribute differently with logarithms, without logarithms, to G-2 of the muon. So this is a kind of very neat example of this whole formalism. Okay, then let us stop here. Or should we go on? No, we shouldn't. Thanks a lot, and see you next time.
إذن هو هنا لم يجري حسابات وإنما يجري عمل مقارنات بهذه الانتجريشن اللي هو عملها كلها في السوفت انتجريشن بالنسبة للأكشن أو الجرين فانكشن عملها في السوفت انتجريشن. أنا كنت أظن أنهم سيكتبوا المعادلات النهائية في هذا الأمر حتى نقارن بما توصل إليه، لكن هو اكتفى بأنه قارن فقط، عمل مجرد مقارنات فقط. والمحاضرة القادمة سيكون هناك رؤية أخرى كما قال رينورماليزيشن. بعد ذلك المحاضرة التي بعدها ستكون عن الجي ماينس 2 فاكتور، وهذا مهم جدا جدا بالنسبة لأعمالي أنا وبالنسبة لي. طبعا عندي أعمال مسبقة للجي ماينس 2 فاكتور بالمناسبة، يمكنكم الرجوع إليها في قناتي. قدمت أعمال أخرى وفسرت أن التذبذب في الجي ماينس 2 أو التغير في جي ماينس 2 ناتج من الجاذبية، وذكرت أن الجاذبية الأرضية، ولكن أعتقد أنها الجاذبية الشمسية. وإن شاء الله في المحاضرة بعد القادمة أو القادمة ذاتها يعني سنحاول أن نثبت ذلك، أن الجاذبية هي التي جعلت هذا التغير في الجي ماينس 2. وافتكر العلماء في فيرمي لاب أنهم اكتشفوا فيزياء جديدة، لكن هي ليست فيزياء جديدة بمعنى، هي فيزياء جديدة بالنسبة لهم هم، لأنه حتى الآن الجاذبية لم تدخل في ميكانيك الكم، وإذا أدخلت في ميكانيك الكم هذه تعتبر فيزياء جديدة، لكن في نظريتي ناتجة من الجاذبية. وذكرت أنها الجاذبية الأرضية. بس إن شاء الله لما نصل إلى تلك المرحلة سنقارن هل هي الجاذبية الأرضية ولا الجاذبية الشمسية بإذن الله تعالى. السلام عليكم.